Hi, I'm Rich Stoll. Welcome to Stall Spin Awareness. You're about to see one of a series of accident prevention safety seminars I've been conducting across the country for the FAA. This seminar addresses the stall spin awareness training requirements outlined in the FARs. You'll also see actual flight footage used to illustrate and clarify many of the points discussed. As always, if this video prompts you to take some hands-on spin training, please be sure you're comfortable with your instructor's qualifications and only use the appropriate equipment in the appropriate airspace. I open my seminars by showing a video clip of a Cessna 150 spinning high above the Santa Clarita Valley near Santa Paula, California. Let's view that clip now and then continue with the seminar. This airplane is spinning, but is it really out of control? Year after year, National Transportation Safety Board statistics show that the majority of aviation accidents occur during day VFR conditions, and many can be attributed to pilot error. If you were the pilot in command, would you know how to get yourself and your passengers out of this situation? Okay, the first three comments I'll make are: one, yes, we do eventually recover from the spin. The second is this is a standard Cessna 150. It is not an Aerobat. There's nothing unusual about the airplane other than given the right conditions, the airplane will enter a spin and stay in a spin just fine until the pilot does something to recover. And the third comment is, by the fourth take, yes, I wasn't feeling very well. Okay? So having said that, to start off a discussion on stall spin awareness, I'm going to just review a little bit of the history of how we are to the point we are now in time with the latest changes to the regulations, and just point out some of the key points in history. And we have to go back to 1912 to a British test pilot by the name of Wilfred Park, who one day while testing an airplane inadvertently entered a spin, and being a good test pilot, he tried to figure out, well, gee, how am I going to get out of this now? And he played around with different control inputs, and he identified the application of opposite rudder as being critical for recovering from the spin. And he actually recovered from this inadvertent spin about 50 feet above the ground. So he landed and he started to tell people what had happened. And so actually once people realized they could recover from these things, they became an evasive maneuver used during World War I. And by 1917, spins were actually introduced as part of primary pilot training. Just after World War II, general aviation was booming, and the government was under pressure to make some changes to the regulations. First of all, airplane manufacturers wanted to be able to design more maneuverable airplanes, and in order to do that, they had to sacrifice a little bit on stability. Well, the stability problems would show up typically during stall or spin type configurations, so they put some pressure on the government to relax the current spin training requirements, spin testing requirements. And also the government was under some pressure to try to reduce the number of fatalities in general aviation that were attributed to stall spin accidents. And at that time, it was about 50% of all fatalities were due to stall spin accidents. So based on those two elements, one being statistics based on pilot accidents and the other being manufacturer requirements to try to build faster, higher performance airplanes, 1949, CAR Amendment 20-3 came out, and it actually eliminated spin training from the primary pilot syllabus. And the emphasis was placed on stall awareness training. And the government was also hoping that airplane manufacturers would take it upon themselves to build airplanes that were more spin resistant. Unfortunately, that didn't really happen. And so by 1991, effective April 15th of this year, FAR Amendment number 90 came out, went into effect, and it requires now stall spin awareness training. Okay? And these levels of training for stall spin awareness affect everybody at some point in time. They affect recreational pilots, private pilots, commercial, glider, and eventually CFI applicants who will have to actually do spin training in order to get their CFI rating. Well, based on this brief little overview of the history, we can make a couple of different, come up with a couple of different points. First of all, historically, it seems about every 40 years something significant happens as far as stall spin awareness. So based on that, I figure about the year 2030 we'll have spin training required again for all primary pilots. Even though part of the reason that they deleted the spin requirements back in 1949 was to try to reduce the number of fatalities due to stall spin accidents in general aviation community, still today, we're faced with the problem that annually stall spin accidents account for the greatest number of fatalities. If you're going to die in a general aviation airplane, more than likely it'll be in a stall spin accident. So that still hasn't changed, although the percentage has dropped dramatically from the 40s. Also, the majority of stall spin accidents occur during the critical flight phases, which we might expect during takeoff and landing, where a pilot is low, slow, close to the ground, high angle of attack, and has a lot of distractions, like obstacles and other people in his way. And the last comment we can make is that almost all stall spins are pilot-induced. And the reason I don't say all stall spins are pilot-induced, we have to leave room for the occasional act of God that might come in and do something, make the airplane enter a spin all by itself. Very, very rare that something like that might happen. Typically, it's the pilot that asks for the situation, and the airplane responds by entering the inadvertent stall spin. Along those same lines, I want to also further review a summary of the spin requirements for airplanes and pilots over the years. And I've broken it down by 3 categories. The first one is the time period. The second category is the normal category airplane spin testing criteria. And the third column is the pilot spin training. And let's see how the 2 elements mesh. How does airplane design mesh with pilot training? Well, prior to FAR CAR Amendment 20-3, 61549, a normal category airplane had to undergo a 6-turn spin test. Okay, and the test pilot at the 6th turn, all he had to do was let go of the controls completely, take his hands off and his feet off, and the airplane had to recover from the spin. If it could do that, it was classified for use in the normal category. In addition to that, pilots were required to demonstrate proficiency in spin entries and spin recoveries during primary training. So not only did you have a situation where airplanes would fix this problem for you if you didn't know anything, they took it upon themselves to also train pilots how to enter spins and how to recover from them as well. Well, once spin training was deleted in 1949 until April of this year, 1991, what they did was for normal category airplanes, they relaxed the spin test requirements, and now they're under the restriction of a 1-turn, and I put it in quotes, spin test. All right, essentially, spin testing was deleted for normal category airplanes. A 1-turn spin, you can read in the flight training handbook or talk to anybody who does a lot of spins. A 1-turn spin is not a spin. It is nothing more than a test of the airplane's controllability in an abused or an aggravated stall. Okay, it is at the very most a very, very young spin. Okay? And in addition to that, if in that 1-turn, if the test pilot can move the controls in some normal fashion to effect a recovery, then the airplane is classified okay for use in the normal category. Unfortunately, on the pilot spin training side, no spin training was required. And in addition, the spin endorsement for CFI applicants was actually optional. You could go take your check ride and not have a spin endorsement in your book. All right, so we have a situation where airplanes, normal category, are not spin tested, first of all, and second of all, the pilot has to know what to do to get it out of a spin, but on the training side, we don't need to teach you how to do that. So in an effort to try to balance it out, to try to put spin training compared to airplanes that aren't having to go through a spin test versus no spin training against airplanes that would fix a spin if you just simply let go, the latest changes that came out address the pilot spin training issue by requiring increased stall spin awareness training. So at least now, at some point in your training, a CFI is going to have to sit down with a pilot and go through a specific ground school session that addresses the scenarios that might lead to an inadvertent stall spin accident. The CFI has to address spin dynamic issues and has to give you at least on the ground theoretically what to do in the case you might enter a spin, how to recover from this thing. During the flight portion, the CFI has to come up with realistic distractions during critical flight phases, and we're going to review what some of those critical flight phases might be. You don't actually have to do a spin, but at least you have to be taught a little bit of the theory behind them, entries and recoveries as well, and the conditions that might lead to a spin accident. CFI applicants, spin training is now required. You have to have the endorsement before you go take the check ride. And not only do you have to demonstrate proficiency in entering and recovering from spins, but you have to be able to teach the students now about spins and spin dynamics. And if you fail the check ride because of deficiencies in your oral presentation of spins and spin dynamics, or the actual flight test deficiencies in demonstrating stalls, when you go back for the retest, you will be required to bring an airplane that is approved for spins, and you will have to do spins for the examiner on the retest. There's no two ways around it. So it pays to know and be proficient in spins before you go for the check ride the first time. Okay, the next part I'm going to review a little bit is the critical flight operations that require maximum stall spin awareness. And as we said earlier, those cases typically occur in the traffic pattern. And we'll talk about a couple of the different scenarios. And the first scenario we'll talk about is on the departure phase. Short field takeoffs, again, low, slow, close to the ground, high angles of attack, maybe maneuvering to avoid obstacles. If we get a little cross-controlled in a stall situation, might enter an inadvertent spin. The engine failure on takeoff or climb out, that tends to be a distraction when things go quiet all of a sudden when you didn't expect it to. All right, if the pilot doesn't react by pushing to lower the angle of attack and to get best glide speed, if he reacts instead by pulling and cross-controls a little bit, could enter an inadvertent stall spin. There's also the scenario after an engine failure on takeoff of trying to turn back to the runway. Okay, very, very dangerous situation, critical maneuvering close to the ground. And ironically, Wilfred Park, the very same man who identified the rudder as being critical for spin recovery, a couple months after making that discovery himself was fatally injured turning back to a runway after an engine failure on takeoff. So he had a lot of insight as to how to get out of a spin, but not very much as to how to get into it. All right? Don't turn back to the runway, land straight ahead, pitch the nose forward for best glide speed and a lower angle of attack. Flying in the traffic pattern, we have two scenarios. One would be overtaking slower traffic. Again, a distraction. Not properly controlling your airplane to try to avoid an airplane in front of you that may be slower. The cross-control turns from base and final. All right, the most notorious being the skidded turn from base to final, which claims pilots' lives every year. And what I'm going to do is I'm going to describe that scenario using the model first, and then I'm going to reinforce it by showing some video of our Cessna 150 in the traffic pattern at Santa Paula going through the same type of scenario. But let's say a pilot is making a base to final turn, and he's overshot the runway center line. Either he's flying a tighter pattern than normal and he just simply misjudged the turn, or he has very strong winds working on him and they forced him to be further in the pattern than he really wanted to be, and he's not able to line up on the center line. Typically what a pilot will do close to the ground is not add any more bank angle because he doesn't want to this close to the ground. So what does he do? He starts to feed out some rudder. All right? And what the rudder does, it has two responses to the airplane. The first response is the rudder yaws the airplane. It moves the outer wing into the relative wind, and it pulls the lower wing away from the relative wind. So essentially, the top wing has more wind on it than the bottom wing. More wind on the wing translates to more lift, and what happens? The airplane begins to roll in the direction he didn't want to add any more bank in the first place. All right, so the pilot typically will respond by applying some opposite aileron. The other mistake, or the other reaction, by applying the rudder in the direction of the turn, is the airplane begins to yaw and the nose drops down. Pilot says, I don't want the nose down, I want it up, so what's he going to do? Start applying back pressure. The back pressure tightens the turn, increases the angle of attack, increases the G-load. In this configuration, if the pilot gets to critical angle of attack, he's got rudder sticking out, opposite aileron at the stall, the airplane snaps into a spin close to the ground. And the airplane does exactly what the pilot asked it to do. All right? Unfortunately, the pilot was trying to get the airplane to do something else other than spin. Okay? And this is how the scenario develops. What I'm going to show you on video now to reinforce that is our Cessna 150 that you saw earlier, performing the same kind of inputs on the base to final turn, and it picks up after the pilot has applied rudder in the direction of the turn. He starts to get some roll coupling in the same direction. The rudder also creates a secondary roll in the same direction as the turn. This increases the angle of bank. To correct this, the pilot applies opposite aileron. This process continues, more rudder, more elevator, more opposite aileron, until critical angle of attack. At this point, with power on, opposite aileron near the stall, and lots of rudder near critical angle of attack, the airplane crisply enters a spin without warning. Skidded turns have yaw coupled with roll. All that's necessary is critical angle of attack to ensure a clean spin entry. The pilot in our example made several mistakes. The first was not knowing that elevator is the turn control. He also misinterpreted yaw and pitch due to two-dimensional thinking. Okay, the other comment I want to make, if I can get this to stop.
A side-by-side.
Okay, is that everything you see on video here is done legally. All right, there's some Hollywood involved. We are not actually in the traffic pattern at Santa Paula and spinning at a traffic pattern altitude. All right, everything we do is done legally, a little bit of Hollywood to dramatize the scenario. I just want to clarify that right up front. Okay. The other scenarios that we can talk about, final approach phase. Again, an engine failure on final approach. If the pilot doesn't react quickly by applying forward pressure to lower the angle of attack and get to best glide airspeed, if he reacts by applying back pressure to a higher angle of attack and cross controls, maintaining improper airspeed on final approach, the airplane can inadvertently stall spin. Also, flying behind the power curve, getting into a very high sink rate or a mush with lots of power in, perhaps not quite as coordinated on the rudder as you should be, and getting into a mush situation that could enter an inadvertent stall spin. Go-arounds, 3 different scenarios. One would be going around with full nose up trim. All right, the pilot applies full power and doesn't compensate for the increased prop wash on the tail and the increased trim effectiveness, and what happens? Nose pitches to a higher angle of attack. As the throttle comes in, the stick or the control wheel has to come forward to keep the pitch attitude from getting to a higher angle of attack and possibly entering an inadvertent stall spin. A go-around with premature flap retraction. We've all either done this ourselves or had somebody sitting next to us do it on us, or at least been on the ground and watched somebody in the pattern go through this scenario. Pilot comes in, let's say in a Cessna 172, has 40 degrees of flap sticking out, decides to do a go-around, adds full power and brings the flap handle all the way up. What happens? The airplane starts to settle out of the sky. Flaps come up, airplane comes down. All right, bring the flaps up on a go-around one step at a time, incrementally. Also, the last scenario on the go-around would be a go-around from a slip on final approach. Now, inherently, slips are spin resistant because a proper slip doesn't have yaw and roll coupled together. It has yaw moving in one direction and roll moving in the opposite direction. It's inherently a spin resistant configuration. And if we're in this type of a slip, let's say we have a right crosswind, so we've got the right wing down, got some left rudder sticking out, and the pilot decides, okay, I'm going to go around from this situation. Adds full power, but doesn't coordinate the aileron and rudder inputs to line the airplane up with the runway again. Let's say he's a little slow on kicking the rudder out, and in fact, when you add full power, you have to go from lots of left rudder over to lots of right rudder because of all the engine effects now by the application of power. If the pilot is slow with the rudder inputs to cancel the yaw, but takes the aileron input out, the airplane can quickly roll over into a skidded scenario and possibly enter a skid spin out of a slip by applying full power to go around and not coordinating aileron and rudder inputs back to neutral. Well, the number one rule after all of this that's pounded into us time and time again is that we've got to fly the airplane. Regardless of what's going on inside or around the airplane, we have to fly the airplane. Our probability of surviving any kind of an emergency is going to be a direct function of how well we implement this golden rule of flying, not how well you can tune in a VOR or read a map or talk on the radio. It boils down to how well you fly the airplane. Well, in order to be able to fly the airplane properly, we need to know how to communicate with it. And so what I'm going to do is spend a few moments just to review what the controls really do. And rather than thinking in terms of the pilot and the airplane versus the horizon, let's internalize all the movements of the airplane and base all the movements, all of our control inputs on how the airplane responds relative to the pilot, not the horizon outside. Okay? And we'll see how this will help us as we go along. First one we'll talk about will be ailerons. And we know ailerons control roll or bank, 2 words for exactly the same kind of motion. All right, a quarter roll and 90 degrees of bank are the same thing. Well, relative to the pilot, if you input the ailerons and watch how the nose moves, it moves from the pilot's head to the pilot's hip. If you take a look out at the wing and watch how it moves from the pilot's head to the pilot's hip. And it will always do so. You can fly the airplane straight up in the air, put the aileron in, take a look out at the wing, and it still moves from your head to your hip. Completely different attitude, but the motion of the airplane is identical, always the same. Okay? Next control surface we have is the rudder. Rudder controls yaw or side slip. Again, 2 words for exactly the same type of motion. And really, the primary function of the rudder is to cancel yaw. If we can cancel yaw, regardless of whether we're stalled or unstalled, if we can cancel yaw and keep the airplane coordinated, it simply will not spin. Okay? Easier said than done a lot of times, but it really boils down to how well we can control yaw. And we do that with the rudder. Well, if we take a look at what rudder inputs do to the airplane, watch what the nose does. It moves from ear to ear. Take a look out at the wings, and they also move ear to ear. Put the airplane in any attitude you'd like, kick in the rudder, it still moves ear to ear. This is how an aerobatic pilot learns to do the things he does. Okay, he internalizes the motion of the airplane relative to him. And we can see if we go back to the skidded turn scenario where the pilot applies the rudder, even if he didn't really know what to do to increase his turn rate to get back lined up with the runway, if he knew that yaw is an ear-to-ear motion, if he kicked the rudder out by mistake and saw this motion and didn't think in terms of up or down, but thought in terms of it's moving to my ear, that means yaw, that's not what I meant, could have avoided the skid spin scenario, okay, by applying some opposite rudder or getting off the rudder. And really the best way to handle that would be just roll the wings level, go around and try it again. Nobody says you have to get on the ground the first time. We all learn to fly to stay off the ground, so don't be in such a hurry to get back. Next control surface we have is the elevator. And elevator controls a lot of different things for us. Sometimes it controls up or down. Usually it does not. All right? A more general way of thinking about pitch, apply back pressure, the nose of the airplane rotates towards your head. Apply forward pressure, rotates towards your feet. Put the airplane in some other attitude, apply forward pressure, where does it go? Towards your feet. In this case happens to be up. All right? Put the airplane in this attitude, apply back pressure, where does it go? Toward your head. All right? Certainly not up in this condition. Right? So think of pitch in terms of head to feet movement of the airplane. Elevator also controls our angle of attack. So the first thing we're going to learn when we talk about stalls or review stalls is it has a whole lot to do with our elevator position. Want more angle of attack? Apply more back pressure. Want a lower angle of attack? Apply some forward pressure. Elevator also controls airspeed in steady state flight. Steady state flight happens to be most of the maneuvering we do in the traffic pattern. So if you want to speed up, a little bit of forward pressure. You want to slow down, a little bit of back pressure. Elevator also controls G-loads. And G-loads really are a measure of how heavy am I right now. You want to feel heavier in the airplane, apply more back pressure. Want to feel a little bit lighter, apply a little bit of forward pressure. All right, so how heavy we feel in the airplane is also controlled by elevator inputs. The elevator also controls what I'm calling circular flight. And circular flight includes any kind of turn you want to talk about and any kind of a loop. All right? Rudder certainly doesn't turn the airplane, but neither does the aileron. Okay? Elevator is the primary turn control. We use the aileron basically to establish the character of our turn. Do we want a steep turn, a shallow turn, a medium bank turn? Do we want an inverted turn? What kind of a turn do we want? Well, we use the ailerons to establish the character. Of course, as soon as we apply ailerons, we need a little bit of rudder to cancel adverse yaw, because that's what the rudder is designed to do. Once you get to the angle of bank that you want, ailerons and rudder have to essentially come back out. If they didn't, you'd keep on rolling. That's how an aerobatic pilot can do a full roll. It just keeps the aileron in longer, that's all. Once you get to the angle of bank, the quality and the shape of your turn is determined by how well you use the elevator. Apply just enough pressure, you can do a level turn. Apply too much pressure, you can start a climbing turn. Not enough pressure, we'll have a descending turn. If you're flying an aerobatic airplane and you're aerobatically inclined, you can even do in this configuration here a loop that's inclined on its side. And if you're real brave, go ahead and push and do an outside loop, leaning on its side. All right, so at 30 degrees of bank, we have a lot of different opportunities for circular flight, not just the straight and level turn. And in fact, another type of turn would be a 0-degree angle of bank, 360-degree turn, which is just a conventional loop, nothing more than a vertical turn, all controlled by the elevator. So in the final analysis, roll, yaw, and pitch movements are attitude independent. Has nothing to do with the horizon outside, has a whole lot more to do with how the airplane moves relative to the pilot in the cockpit. And if we try to internalize it in this way, we can avoid some of the miscommunication between the pilot and the airplane and avoid possibly inadvertent stall spin accidents. In keeping with this, what I'm going to talk about next will be the 3 S words in flying. The 3 S words being a spiral, a stall, and a spin. All right? 3 types of scenarios that we need to know how to respond to quickly and appropriately in order to recover from them and get back to what we call normal flight. And what we're going to find is that each one of these controls will be primary for recovering the airplane from one of those three scenarios. All right? And on video in a moment, I'm going to show you a side-by-side comparison of a spin next to a stall and then a spin next to a spiral, so that it's clear in everybody's mind that the three maneuvers are completely different. They look different, they feel different, they sound different, and the reason we get into them are all different, and the way we get out of them are different. Okay? The control inputs we make are different in each one. And basically, a spiral occurs below critical angle of attack, and it really has to do with an overbanked configuration. Too much angle of bank for the amount of elevator authority. So the only type of turn you have available to you is a steep descending turn. And what happens, the tighter you pull, the tighter the turn becomes. All right? And so actually pulling on the elevator aggravates a spiral situation, and a couple of other things occurring. You're losing a lot of altitude, gaining a lot of airspeed, and the more you pull, the heavier you start to feel. So gaining increasing G loads. And you eventually run out of altitude or get to a point where airspeed and G load combination doesn't work so good anymore, and you start losing things off the airplane. All right? And what we'll find is the ailerons are primary for recovering from the spiral. We'll talk about that in a moment. The stall is purely a function of the angle of attack of the wing. Exceed critical angle attack, the wing stalls. It's that simple. Doesn't matter what attitude you're in or what airspeed, provided you're at or below maneuvering speed. All right? So purely a function of what we've done with the elevator. A spin occurs above critical angle of attack, and really it occurs because we've done an uncoordinated stall. We've allowed yaw and roll to couple together, and the yaw-roll couple above critical angle of attack induces the autorotation. It allows it to occur. All right? And a rudder will be primary for recovering from the spin, as we'll see. But also in the spin, it's characterized by a constant G loading. It's not increasing like in the spiral. It may be 1 G if it's a normal upright spin, or it may be 2 Gs if it's some kind of an accelerated or an aggravated spin mode, but it'll be relatively constant. And so will the airspeed. It'll be low and constant. So that's the difference between the spin and the spiral. And what I'm going to show you on video is a side-by-side comparison so that it's clear in your mind what is going on in each one, and then we'll talk a little bit more about how to recover from each. A side-by-side comparison of a spin and a stall reinforces this. Notice how the spin moves in a tight, rotating, but predictable descent with a yaw plus roll type of motion. The stall moves in a more even, but less stable descent with lots of changes in pitch attitude. A side-by-side comparison of a spin versus a spiral clearly shows their differences. Spins begin with tumbling gyroscopic instruments, high rates of descent, rapid but constant rates of altitude loss, and low but constant airspeed, which is due to the high drag configuration of the spin. Airspeed will stabilize and remain constant regardless of the number of turns in the spin or how much altitude is lost. Spirals are steep descending turns in which the gyroscopic instruments may not be tumbling. The altimeter unwinds at high and accelerating rates, and the airspeed quickly increases to very high values. Spirals occur below critical angle of attack with relatively little drag to resist airspeed buildup. From the outside, spins appear to rotate in a near constant manner around an axis that passes close to the airplane's center of gravity. Spirals appear to accelerate around an axis located near the wingtip or in the center of a circle around which the airplane is flying. And now we'll spend a few moments just to talk about how we get out of these different maneuvers if we inadvertently enter them. Under the heading of emergency recovers, the first one we'll talk about will be the spirals. Ailerons are the primary recovery control from spirals, and the way we teach spiral recovery is like this. Think of it in terms of power, push, roll. Since we're descending and the airspeed is increasing in a big hurry and the G load and the altimeter is unwinding, reduce the power to idle, power off. Second thing you want to do is push. And I don't mean push yourself through the roof of the airplane. Push to unload the G load, unload the wing, lower the angle of attack. The more pull you have, just the more aggravated the spiral will become. Unload the wing with a little bit of forward pressure on the elevator. Next thing you want to do is the primary recovery control input, and that's roll to wings level. And we roll with lots of aileron and some coordinated rudder to cancel the adverse yaw. Right? Unfortunately, what happens when pilots get into adverse situations like a spiral is they respond to the pitch attitude, and they try to fix the pitch attitude all the time. Well, in the spiral, more pull just aggravates a spiral. It doesn't fix the pitch attitude. All right, so I want you to think, whenever things are going wrong in the airplane, worry about the pitch attitude last. Fix the other problems first. The first problem in the spiral is that we've got too much angle of bank. So we've got to fix that first. Power off, push, unload the wing, roll to wings level. Now we can fix the pitch attitude, pulling back to straight and level. So always worry about the pitch attitude last. Fix the other problem first, okay, rather than reacting with a pull. The next area that I'll talk about will be the stalls. And as we saw, stalls are purely a function of the angle of attack of the wing. And so the elevator is the primary recovery control from a stall. You want to unstall the wing, or relax the elevator a little bit. Don't hang on to it. Again, don't react to the pitch attitude. When the nose starts slipping away from the pilot, what do they typically do? They apply more back pressure to fix the pitch attitude. Don't worry about the pitch attitude. You have to fix the stall first. We need to maintain our heading and our wings level with rudder inputs, and we'll talk about why that is in a moment. Lower the angle of attack with elevator inputs. And think of it like this. The nose and the stick or the control wheel have to move in the same direction all the time when we're flying the airplane. Think of what happens when you practice a power-off stall. You apply back pressure. Where does the nose go? Toward your head in the same direction that you're pulling, right? What happens at critical angle of attack if you're flying a properly loaded airplane? The nose pitches the other way. It moves in the opposite direction of the stick. If you apply more back pressure, what happens? It moves even further, and the stall becomes more aggravated. As soon as the nose shifts directions, so do you. Reach for the nose with the stick of the airplane. That goes to lower angle of attack. Once you've caught up with it again, then we can recover the pitch attitude. All right? So on stall recovery, think about moving the nose and the stick or wheel in the same direction all the time. All right? And it's very important to maintain your heading and your wings level working rudder inputs. And we'll talk about why that is right now. And what I'm going to show you are the typical stall patterns for various wing planforms. We'll see what goes on when the wing stalls. And the first wing I'm going to talk about will be the rectangular planform, which is very typical on most of the primary trainers that we have. The rectangular planform is not very maneuverable, and so what does that mean? It's probably pretty stable. And when it's flown correctly, that's what we see. Not much maneuverability out of a Cessna 152 or 172, but relatively stable. And what happens during a power-off stall in a rectangular planform, the airflow begins to separate at the wing root first. And that gives us a couple of added benefits. First of all, the turbulent air spills off the wing root. It hits the fuselage of the airplane in the tail section. That's where we get our aerodynamic buffet. So we get good stall warning with the rectangular planform. The other thing it affords us is good lateral control, good aileron control a little bit longer. The aileron sitting out at the wingtip, well, if the stall starts at the wing root and progresses outward, we can use the ailerons a little bit longer until the stall gets out into that area, at which time we don't want to use the ailerons anymore because they can actually aggravate the situation. All right? So very, very stable configuration, rectangular planform, desirable stall characteristics. In a power-on stall, however, the slipstream from the propeller may delay separation of airflow at the wing root. And in fact, it may occur a little bit further out. You may lose aileron control a lot sooner in a power-on stall than a power-off stall. And you may not get the good aerodynamic warning that you get in a power-off configuration. Well, if we move to a little higher performance planform, the moderate taper, a little higher performance, so that means a little less stable. And the characteristic of the moderate taper planform is that it tends to stall throughout the span all at once. So right away at the stall break, you lose lateral control. Ailerons aren't so effective anymore, and so now we have to think about leveling our wings with the rudder right away. So it requires a little bit more rudder work at the stall break. And the third planform I'll talk about will be one that has sweep back. A swept wing is a very high-performance airfoil, very maneuverable, all right, and therefore not very stable. And the characteristic of the swept wing is that it will stall at the wing tip first. Very violent stall characteristic, all right? And what happens, we lose lateral control, aileron effectiveness right away, immediately at the stall. But also, by stalling out at the wing tip, if it's severe enough, we can shift the center of pressure of the wing ahead of the center of gravity of the airplane. And what can happen, the airplane can diverge into a pitch-up mode, into a higher angle of attack, and become non-recoverable. All right? So very maneuverable, but not very good stall characteristics. Now, one of the interesting things is that we can get a rectangular planform to act like a swept wing planform in terms of stall characteristics. Anybody know how we do that? Go ahead and yaw the airplane. Okay, if you yaw the airplane, the airflow starts a cross flow along the wing, and it begins to take on the characteristics of a swept wing. So you can start to see how important the rudder really is. Right? We can take a relatively docile planform, and by mishandling our yaw control, turn it into something much more aggravated. And in the skidded scenario, what's happening? The pilot has lots of yaw. Okay, he's got a planform that could be acting like a swept wing with a stall somewhere out at the wingtip and a very violent roll into the spin. And if he's got some opposite aileron as well, it will further aggravate it and make an even crisper entry. If you ask an aerobatic pilot, you know, what's a good way to enter a spin, he'll probably tell you to do something very similar to that. Okay? So the rudder is very, very crucial, especially in our lower performance airplanes, to keep our planforms to work the way they're designed to work. Favorable stall characteristics. Okay? What I'm going to show you now on video is just some normal stalling back to our emergency recoveries in our Cessna 150, making the nose and the control wheel move in the same direction. And one of the ways we teach our pilots to do our stalls is not only looking over the nose, but also they can do an entire stall entry with recovery looking out at the left wing only, or looking out at the right wing. They can do the entire process without having to look over the nose, because if you inadvertently enter a stall, who knows where you're going to be looking? So it's good to have a lot of different sources of information. So the first clip I'll show you will be just looking out the left wing of a Cessna 150 going through a power-off stall, and you won't see any gross pitch changes. It'll be just enough to enter the stall and just enough to recover from it.
All right, working power back. Going to hold the altitude by applying back pressure on the elevator, which will rotate the nose and the wings toward the pilot's head. Critical angle of attack will be somewhere around 16 to 18 degrees, at which point the nose and the wings will pitch toward the pilot's feet. Stall, nose and wings pitch, relax back pressure on the elevator, apply power to recover straight and level.
Okay, the next piece of video I'm going to show you will be the same Cessna 150, now with the camera looking at the tail section. It looked pretty docile looking out at the wing, but the rudder is doing a lot of work to keep everything straight, to keep the wings level and the nose on a heading. And even though in a stall, if the airplane starts to get away, if you try to catch up with the rudder, and sometimes it has to work very quickly, if you're trying to catch up and cancel that roll off of the wing, the airplane might do a lot of different things, but it won't spin. And that's really the importance of proper rudder work near and above critical angle of attack. So we'll take a look at the first sign of the stall. The rudder's not doing a whole lot, but as the stall progresses and becomes more aggravated, you start to see the rudder doing a little bit more movement from side to side. The controls still work during a stall, but they are less effective than they were below the critical angle of attack. Elevator and rudder must now work in the lumpy air spilling off the wing, and we expect them to be less effective in controlling angle of attack and yaw, and this is in fact what we observe. So sometimes the rudder's working pretty hard back there to keep the airplane from rolling off into a spin, and as long as we can coordinate our stall entry and stall recovery, the airplane won't spin. That's what it boils down to. The one other aspect of stalls I want to clarify and spend a little bit of time on is the relationship of the stall to airspeed. Right? We all learned during our primary training that an airplane can stall at any speed and any attitude. Unfortunately, most of our training concentrates on one attitude and one airspeed. So unfortunately, what we hear and what we've experienced generally are two different things, and typically a pilot will think he's safe if he stays away from his experience, which is one attitude and one airspeed. The diagram I want to relate airspeed to is called the VG or VN diagram, and it's contained in the back of your flight training handbook in the last chapter on aerodynamics, which nobody ever gets to read, but has a lot of very good information in it. This diagram depicts the relationship of airspeed and G-load, all right? And in fact, what we'll find is we need the combination of airspeed and G-load instantaneously to know what our angle of attack is. We can't just rely on airspeed alone. We need to know two things. All right? And what we've plotted here is positive G's as a function of airspeed. And we can draw the same kind of picture on the negative G side, but just to make it easier, we'll talk on the positive side. And we can draw a line that represents critical angle of attack or stall. I've also represented a dotted line that shows 3.8 G's positive, which is the normal category limitation, all right, where the airplane is now becoming structurally limited to what we can do with it. The one speed we can point out on the graph is VSO. And that's the airspeed that typically most of us learn to do our stalls, which is the stall speed in the landing attitude. The one thing that's not reinforced when we're doing our stalls at this airspeed is what's our G-load? Our G-load is 1. If you're at 1 G at this airspeed, you're going to exceed critical angle of attack. But unfortunately, the G-load that corresponds to that airspeed isn't reinforced strongly enough. And we can see there's a whole range of G-loads and airspeed combinations that will exceed critical angle of attack. All right? The other key V speed that we can show on this diagram occurs where the stall line intercepts the structural limit of the airplane, 3.8. Does anybody want to guess what that V speed is? It's an important V speed to us. Okay, very good. Must have a bunch of instructors or people that read a lot more than others. Yes, maneuvering speed, V sub A. What is maneuvering speed? It's the maximum speed at which we can make full or abrupt control deflections. Why? Because the airplane will stall instead of bend or brake, right? And in fact, at or below maneuvering speed, the stall is an aerodynamically good thing for the airplane. It keeps us heavy-fisted pilots from braking it all the time. All right? Above maneuvering speed, we're limited structurally. We may bend or brake the airplane before we ever exceed the critical angle of attack. What do airplane manufacturers recommend in turbulent air? Some speed at or below maneuvering speed, right? Because if you are doing a maneuver and you get a gust load or a turbulent encounter, the airplane will stall instead of brake. All right, now I can... Pardon me?
Maneuvering speed is also adjusted for weight.
Yes, that is correct. As the airplane's weight changes, this whole picture will change as well, up or down, depending whether the weight goes up or down as well. The important thing is, at any speed below maneuvering speed, we can stall the airplane given the right G-load combination. And in fact, in our skidded spin scenario, we're not at VSO. Very, very few, if any, stall spin accidents occur at VSO and 1G. They occur during some kind of a maneuver where the pilot is at a higher G-load and therefore at a higher stalling speed. Okay, and if you look in the performance charts in the pilot operating handbooks, what happens? As angle of bank increases, so does stall speed, right? Why? Because the G-load necessary to sustain the turn at the higher bank angle increases. G-load increases, stall speed increases. All right? And I can only guess, I don't know from my own experience, but I believe it's a whole lot easier to learn how to enter and recover from a stall than it is to learn how to bail out of an airplane that doesn't have any wings on it anymore. Okay? The stall is a good thing for the airplane, believe me. Okay? So it behooves us to learn how to cope efficiently with them. And it's quite possible to even fly slower than VSO, provided the G-load is less than 1. And we can do a practical demonstration of that. Take your Cessna, your Piper, whatever, gain a little bit of speed, pull it up into a nice little climb, let the speed bleed off, and then very easily push. Go a little bit light in the seat, a little bit ballistic. And what happens? The G-load goes down, we can watch the airspeed go right down to the peg and not stall the airplane unless we try to load it up again. All right? In fact, the aerobatic pilot performing a hammerhead turn at the top is at virtually 0 airspeed and 0 G-load. He's pivoting the rudder against the slipstream of the propeller, and there is no stall involved whatsoever. 0 airspeed, 0 G-load. And in fact, if you can get to 0 airspeed, you can't stall anyway, right? You have to have airflow to separate to stall. Airplanes sitting on the ramp at an airport are not stalled. They're not generating any lift, but they're not stalled. Okay? So we need airspeed to stall the airplane. All right, the next part we're going to get into now will be spins. And as Wilfred Park discovered way back in 1912, the rudder will be the primary recovery control from spins. And spins don't just occur. They go through a process of development. And I'm going to show you on video the 3 phases of a spin. All right, when a spin first starts, it's in what we call the incipient phase. And depending on the airplane, could last from 2 to 6 turns before it moves from the incipient phase, which means it's turning from a stall into a full-blown auto-rotation. Then it gets to the develop phase. So in airplanes that take 5 or 6 turns to develop in a spin, if they're a normal category airplane and have only done 1 turn, they have only been in a very, very young incipient spin. All right, and it's very important to remember that, and we'll talk about why that is in a moment. But again, this will be just a ground-to-air shot of our Cessna 150 performing a multiple turn spin, and we'll break it down into the different elements of the spin, from incipient through developed through the recovery phase. The spin has 3 phases. The first is called the incipient phase and occurs while the spin is developing. This phase may last anywhere from 2 to 6 turns, and during this phase, the rate of rotation of the spin increases. The second phase is the developed phase, in which the rate of rotation and the nose attitude remain constant. Turn number 10 looks no different than turn number 110. The last phase is the recovery phase, which occurs after the application of recovery inputs. Rotation slows and the nose attitude steepens. This phase may last anywhere from a quarter turn up to several turns. Okay, in the early 1980s, NASA conducted a series of spin tests on some general aviation airplanes. And a couple of things they were trying to study were the effectiveness of different recovery techniques from the spin, but also trying to evaluate what's really going on during a spin. What happens if we move the center of gravity around? What happens if we change the mass loading of the airplane? What happens if we move the controls around during a spin? And they used 4 different airplanes that they thought represented what we, the general aviation community, are flying. They used a Cessna 172, a Grumman Yankee, a Beech Sundowner, and a Piper T-tail Arrow. And I want to talk a little bit about some of the findings on 2 of the airplanes, the first one being the Cessna 172. And I'm going to talk about what happened when they started moving the center of gravity around. And the first picture I'll show you here is the operating envelope for a Cessna 172 that shows center of gravity as a function of weight and defines the operating envelope. Now, the Cessna 172 is a dual category airplane, utility at lower weights and forward CGs and normal category elsewhere. All right, and the first important point I'm going to make is all normal category airplanes, intentional spins are prohibited, all right, because they've only had to demonstrate recovery from a 1-turn spin within 1 additional turn, which really isn't a spin test at all. Okay? And it's very, very important for me to try to convince you and for you to convince yourselves that you do not spin a normal category airplane. Okay? For 2 reasons. First of all, chances are the airplane has not been spun beyond 1 turn, and so if you go beyond 1 turn, there's absolutely no guarantee that it will be recoverable, and you are being the test pilot. You're doing something for free that perhaps the paid test pilot didn't want to do or wasn't required to do. Or perhaps the test pilot did go beyond 1 turn and he didn't like what he saw. Okay? And he had a parachute to do something about it, and if you don't, you know, could be in a lot of trouble. Don't spin a normal category airplane, no matter who's in it with you. I don't care if it's a high-time CFI or an ex-military fighter pilot. Don't let anybody talk you into spinning a normal category airplane. It might recover one day, but it might not 5 minutes later if you try it again. Okay? It's very, very unpredictable past 1 turn. Utility category airplanes you have to be a little bit careful with. Utility category airplanes can be tested one of 2 ways. They can either be spun as though they were an acrobatic category airplane, which means a full-blown 6-turn spin, or they can undergo a spin test as though they were a normal category airplane, which means recovery from a 1-turn spin. If utility category has been tested like a normal category airplane, it will have a placard in it saying intentional spins are prohibited. So that means don't spin that airplane. If the utility category airplane has a placard that says spins are approved, then you know that at least somebody's taken it into the developed phase and it's demonstrated recovery as though it were an acrobatic category airplane. Cessna 172 is approved for spins when operated in the utility category only. All right? So what NASA did was they first conducted some spin tests with the airplane loaded in the utility category. Forward CGs, lower weights, much more difficult to get high angles of attack, a little bit more spin resistant. Okay? And what they found as they started playing around with the center of gravity location is the forward positions in the utility category When the experienced test pilot tried, and tried as hard as he could only get the airplane to enter a spin 42% of the time. Very, very spin resistant, didn't want to go into the spin. All right, and typically, of the spins he was able to get into, at about the second turn, the 172 just popped out of the spin all by itself, without the pilot having to do anything, and transitioned from a spin into a spiral. Very, very spin resistant at the forward limits in the utility category where spins are approved. So then NASA said, all right, well, let's start moving the center of gravity aft. And once they moved out of the utility category, NASA's pretty smart. They said, well, now we're into uncharted territory. Let's put a spin chute on the airplane, which is a special device mounted on the tail section of the airplane, whereby if they inadvertently get into a spin mode that they can't recover from, they can deploy the chute and that'll break the spin. So once they moved from the utility category into the normal category, they so equipped the airplane. In the mid position, they found that they were getting better at entering the spins. They could enter 57% of the time they tried. All right, so it's getting a little bit more likely, given pro-spin inputs, that the airplane would enter a spin. Then they moved the center of gravity and the weight back to the upper corner, maximum gross weight and right at the aft limit, and they could get the airplane to enter 65% of the time. So we can see the character of the spins are changing. The airplane is a little bit more willing to go into the spin at the aft limits. Well, then NASA threw in a little bit of reality, and they said, well, we know pilots are always trying to push the envelope. Let's go ahead and load the Cessna 172 just 5% beyond the aft limit. Just stretch the envelope a little bit and see what happens. And what they found was they could now get the airplane to enter the spin 94% of the time. So the same, perhaps uncoordinated or sloppy type of flying in the utility category, where the airplane would, by design, take care of you for you, those same kind of inputs at the aft limit, the airplane wouldn't fix anymore, but would be more than happy to do what you ask it and would enter a spin. And one of the very critical observations they found back at the 5% aft limit was this. Some of these spins were non-recoverable. Okay, if you didn't have a spin chute, the airplane would go all the way to the ground in the spin. So we can see, we can take a otherwise normally docile airplane, and throughout its operating envelope, it displays very, very different characteristics. Unfortunately, most of the training people get when they're transitioning from a 2-place to a 4-place or so on is what? In the utility envelope. Right? Just an instructor and the student. And the first time they ever push the limits is the day they get signed off and they load in a whole bunch of friends and camping gear and swimming gear and scuba gear and try to take off a Big Bear in the middle of the summer. Completely different airplane. So if there are any instructors out there, one thing you might suggest to your students that are checking out in a 4-place airplane moving up would be to take at least one of those flights and put some other people in the back, and under a controlled environment with the instructor, fly it at the other end of the envelope and find out what it's going to be like. If you're a student checking out in an airplane, you might suggest the same to the instructor. Say, before I really put my family in this airplane and go on a trip, will you find a couple of other people, put in the back seat, and let's go out and fly this airplane how I'm really going to use it. Okay? Might not be a bad idea to keep in the back of your mind. All right, the next piece of video I'm going to show you is some actual NASA footage taken when they were flying the Grumman Yankee. And the Grumman Yankee is a normal category airplane, and so what NASA did right off the bat was they installed the spin chute on it. They didn't want to take any chances. And what they found was, beyond one turn, the Grumman Yankee liked to just go into non-recoverable spin modes. It did it a lot. Okay, so they used the spin chute a lot. And what you'll see is you'll see different camera angles, one camera out at the wing looking down the wing into the cockpit, one camera angle over the pilot's shoulder, one looking back at the tail. The airplane is tufted so you can see kind of what the airflow is doing over the different control surfaces. And then they'll cut in some of the dialogue that the test pilot is having with the ground people, some of the information he's relaying. And we'll see kind of what happens here. The other thing I want to point out is the speed of this footage. The spin might look fast to you, all right? But the cameras were actually set at 2/3 real time. So the real spin the pilot is in is a little bit faster than what we see here.
For years, NASA and the military have been conducting spin research in an attempt to analyze spin characteristics, evaluate spin recovery techniques, and develop spin-resistant airplane designs. To understand the complex mix of variables that determine the dynamics of spins, NASA collects electronic, visual, and audio data during spin tests of general aviation aircraft. Cameras mounted at different stations on the airplane record airflow patterns and control positions. The random and disturbed tuft movements are indicative of the turbulent airflow associated with high angles of attack. Listen as the test pilot relays information during this spin.
5, and she's really spinning up. 6, 7, engine is stopping. There's full recovery controls. Don't see any effect. 7,000. Okay, my hands are off the controls now for a couple of turns. Recovery controls again. First spin, recovery again.
Note the turbulent airflow over the tail section and watch the control inputs used to attempt a spin recovery. This particular test resulted in a non-recoverable spin mode, requiring the use of a special spin chute to stop the rotation. One major benefit of such technical research is the development of spin recovery techniques based on spin dynamics. Although the aerodynamics of the spin are quite complex, the spin recovery procedure can be reduced to a series of simple, effective steps.
Okay, we're going to talk about what the series of simple, effective steps are that NASA identified and actually confirmed during their years of spin testing in the early 80s. And basically it boils down to these 4 steps. First thing we want to do is get on the throttle, take the power, and reduce it. So power off. The second step, ailerons to neutral. Third step, rudder. Find the opposite rudder and push it all the way to the firewall. The fourth step, elevator. Briskly move it through neutral. And that could mean either a push or a pull, depending whether it's an upright or an inverted spin. And we boil it one step down from there into a simple mnemonic called PARE, P-A-R-E. It's sort of like a pilot's gump check. Okay, what am I going to do in this spin to recover from it? And this sequence of events, NASA identified as maximizing the probability of recovering from a recoverable spin. If the spin's non-recoverable, well, it doesn't matter what you do. Okay, but if it is recoverable and you apply these steps, you will maximize the probability of getting out of it with the least amount of altitude lost. Now, a couple of the inputs that NASA played around with during the spin test would be to move the throttle in and out, move the ailerons around, move elevator around, see what happens, how it affected the spin dynamics. And basically what they found during spins is if you add power to try to drive out of the spin, what it does is it increases the rotational energy of the spin. So you get higher rates of rotation. And depending on the airplane, it may actually contribute to flattening the spin mode. So the airplane goes from a nose low attitude to something a little bit higher, a little flatter spin mode. But definitely increased rates of rotation by adding the power. If we don't want to get into that type of an aggravated situation, reduce the power idle right away. Ailerons also had an adverse effect. Applying outspin aileron, opposite aileron to the spin, upsets the balance of yaw and roll in the spin. And what it does is it changes the roll part of the spin into more yaw. And what it does is it begins to level the wings, increasing the rotational energy in yaw of the airplane and further flattening the character of the spin. Opposite aileron in a developed spin has a very, very strong flattening tendency in an airplane. And if you watch an airshow performer, perhaps who opens up his act with a flat spin down to a lower altitude, he's got full power on and he's got full opposite aileron. And if you don't want to do that kind of a spin, get the power off and neutralize the ailerons right away. Okay? In-spin aileron tends to do a little bit something different to the yaw roll component. It takes the yaw component and turns it into more roll. So now we have a spin character that has predominantly more roll, a greater roll look to it. All right? Greater rate of rotation as well by applying in-spin aileron. So in-spin aileron also aggravates or tends to aggravate the character of the spin. If we don't want to do that either, let's go ahead and neutralize the ailerons. Okay? So now we've done a couple of steps that will keep the airplane from going to a flatter spin mode, hopefully, or if it is moving into a flatter spin mode, hopefully take it away from that mode for us. It also sets up the primary input, which will be the opposite rudder. All right, and once you identify the opposite rudder, it's got to go all the way in. It's a very brisk input. You can't move it very slow and take your time with it because it may not upset the spin dynamics. You've got to apply it full in all at once to the stop. Now, it may be a little bit difficult to try to figure out, especially in an inadvertent spin scenario. Obviously, you didn't know why you got in it in the first place, otherwise you wouldn't be there. So you may be a little disoriented and not know which way you're turning. The best way and the best chance you have of identifying the opposite rudder is to actually have gone through a spin once with an instructor. So you can tell which way you're spinning by how the ground is moving. All right? If you haven't done that or you're still not sure, come inside the airplane. Don't use the slip skid ball. It's not reliable. Depending where it is in the airplane and what kind of spin you're doing, could be in spin, could be out spin, or could be pretty close to ball centered. So the slip skid ball is not reliable. Turn coordinator, if it's working properly, will show you the direction of the spin. So now you know where the opposite rudder is. Step on it all the way to the firewall. Okay? Once you've made that input, it's then time to move to the elevator input. And again, the elevator input has to be a brisk input. All right? One of the things the elevator does for us as we're approaching the end of the procedure, first, one thing it does is it lowers the angle of attack of the wing, but it also has an anti-spin contribution through gyroscopic effects. And in some airplanes, in some spin modes, we may need all the anti-spin yaw that the rudder can give us, plus the little bit of anti-spin yaw generated through the elevator input to break the spin. So the elevator input is an important input, and it's got to follow the rudder input. As soon as the rudder's in, elevator is a brisk input at least through the neutral spot. If it's back here in your chest, you've got to push it through neutral. If it's under the instrument panel, you've got to pull it through neutral. All right? That would be an inverted spin if the stick were up under the instrument panel. Not very likely in a Cessna 172 or any Piper. More likely for an aerobatic pilot at the top of a loop. But whichever direction you have to move the elevator, move it briskly through neutral. And we'll talk a little bit about pilot operating handbooks in a moment, but if the pilot operating handbook says to move it full forward or full aft, go ahead and move it there. But it's got to go at least through neutral. Don't hang on to it. Okay, move the elevator. If you don't like the way it looks outside of the airplane, don't look outside. Again, bring it all inside because the spin recovery is going to depend on where we move the controls. Look at the throttle, identify it, and pull it out. Okay, we have students pull the carb heat all the time, and that doesn't cut it. Look at the throttle and pull it off. Okay? Next step is to neutralize the ailerons. If you're flying a control wheel and it looks like that, it's not neutral. Twist it neutral. If you're flying a stick airplane, it's got to be lined up in front of you somewhere. Move it there. Hold the input, find the opposite rudder. If you don't know which way you're spinning by looking outside and you're not sure what the turn coordinator is telling you if you have one, try to sample the rudder. And the only way you can do that is to have had some spin training, because if you haven't, you're probably like this. Both of them feel pretty heavy. Got to be able to sample them. And depending on the tail configuration, you might find a rudder that offers more resistance. That's the opposite one. Step on it with all you've got. Push it to the firewall. Once that's in, like I say, if the elevator is back here in your chest, it's got to push forward through neutral. If it's under the instrument panel, pull it aft through neutral. Once those steps are done, hang on and wait. It may take a few turns for the spin to break. Once the spin is over, neutralize the rudder, and then recover the pitch attitude with a smooth pull back to straight and level. Okay? With this procedure, all the spins, whether they're inverted or upright, will end with a pull back to straight and level. It's also important not to inadvertently move the elevator before you move the rudder, because in the spin, if we apply forward pressure, all right, say in an upright spin, we actually begin to drive the nose closer to the spin axis, which passes through the airplane. And it has a pirouette effect, like an ice skater drawing her arms in during a spin on ice. What happens? Speeds up. And it's even possible to take an upright spin with enough forward pressure to turn it into an inverted spin, which doesn't help much either. Okay? So hang on to the elevator, don't move it until its time, and its time is after the rudder input. All right? And try to remember the simple mnemonic pair. And what I'm going to show you now on video is the worst possible type of spin anybody could imagine, and that's an inverted flat spin with full power stick, full forward, and full outspin aileron. Okay? And then working through this procedure to try to effect a recovery, and you'll see once the steps are done, the airplane pops out of the spin and it's a pull back to straight and level. This airplane is a Pitts S1 performing an inverted flat spin. Whether the spin is upright, accelerated, flat, or inverted, if it's recoverable and you apply steps 1 through 4, power, aileron, rudder, elevator, they will all end with a pull to straighten level. With this procedure, inverted spins do not end inverted. The natural question that comes up next is, well, how does all of this relate to what my pilot operating handbook says? And really, if we're going to discuss stall spin awareness and do it effectively, we can't just blanket statement say, go read the pilot operating handbook, all right, because it may not always be the cure-all that we think it should be. Okay? With the information we now have, we can go back in and read the spin recovery procedure and try to interpret what the airplane manufacturer intends for us to do. And I'm just going to pull out a few different procedures. We'll see the whole range of what's available to read on spin recoveries and see how we have to read between the lines sometimes, and in other cases it's very clear what our job is according to the manufacturer. One airplane I pulled out was the pilot operating handbook, what it says to do in a Cessna 185 Skywagon, 1968. And of course, if somebody says, well, just read the pilot operating handbook, that's the legal thing to do, well, this is what you're going to find. Intentional spins are prohibited in this airplane. Should an inadvertent spin occur, standard light plane recovery techniques should be employed. So now you have all the life-saving information you need, right? Well, we have to take the published procedures with a little bit of grain of salt and really read between the lines. What are they telling us to do? In that case, what are you going to do? I'm probably going to do something like power off, ailerons neutral, opposite rudder, elevator neutral. Let's take a look at another airplane, and I'll title it, Which Procedure Do I Use? And the airplane I'm going to show you now will be the Decathlon. And the Decathlon is a standard aerobatic and spin trainer. We use them all the time at our flight school. And this is what the Decathlon pilot's operating handbook says to do. A little bit different from the Cessna 185. It has clear steps, one by one, what we're supposed to do in a given order. But let's read what it says. Throttle closed, ailerons neutral position, elevator positive forward to neutral, and then rudder full deflection the opposite direction. Well, they've reversed the rudder and elevator inputs that I said NASA identified as being optimum for spin recovery. All right, so what do? Well, we have a little bit of a dilemma. It's pretty clear, you know, what we're supposed to do, but it's a little bit different from what the guy up here said at the seminar. Well, let's take a walk out into the airplane, and let's climb in and take a look at the placard in the cockpit of the same airplane. This is what it says. To recover from normal or inverted spin, use full opposite rudder, then neutralize elevator. So, we can cut them some slack on the placard in the cockpit by saying, well, they're saving space, that's why they didn't say anything about throttle and ailerons. But is it really that insignificant? It doesn't really matter whether the rudder comes first or the elevator comes first as long as we do them all? Well, in our experience, yes, it is. And in NASA's experience, it is as well. All right? Typically, what happens when you apply elevator first, we get the accelerated spin mode. And a pilot in an inadvertent spin situation, if he applies an input and he sees the spin get worse, what's he going to do? One of two things. He's either going to stop right there and never make the primary recovery input, which is the rudder, or the added adrenaline rush is going to require or result in an even stronger push on the elevator and can transition the spin from upright to inverted. Okay? What I'm going to do now on video is show you typically what a student might do to me as the instructor in the decathlon. I'm going to enter an upright spin in the decathlon, and then I'm going to implement the procedure outlined in the pilot's operating handbook instead of the one in the cockpit on the placard. And we'll see what happens. We'll actually transition the spin from upright to inverted.
Watch as the decathlon enters a 2-turn upright left spin and then transitions to an inverted spin to the right. At 1.5 turns, forward elevator is applied, then full right rudder. The airplane slows down, appears to stop, and then quickly transitions to inverted. To avoid the accelerated spin and transition spin modes, apply full opposite rudder first, followed by the elevator neutral.
So we can go from bad to worse in a big hurry. Fortunately, in the decathlon, being an aerobatic airplane, it's stressed for +6, -3. You go through about 2.5 to 3 negative Gs for that transition. If somebody got real strong in a Cessna 150, which is stressed for minus 1.52, you'll break the spin, you'll break the wings, and a few other things. Okay, so you get out of the spin, but you'll have some other problems to deal with. It's important to move the rudder first, followed by the elevator input. And even manufacturers are not clear what procedure to implement. So our final analysis on that is a seemingly minor change in the order of spin recovery events can have a dramatic impact on the character of the spin. Okay? All right, let's take a look at another procedure. Take a look at a typical Beechcraft procedure. It doesn't really matter. They're all cookie cutter from one airplane to the other with Beech. But at least, even though we had some problems with the Decathlon handbook, it was easy to read. It was step by step. We had a little problem with the order of things, but it was a little easier to interpret. Let's take a look at the Beech procedure, a big paragraph. And it starts off, immediately move the control column full forward and simultaneously apply full rudder opposite to the direction of the spin. Continue to hold this control position until rotation stops, and then neutralize all controls and execute a smooth pullout. Aileron should be neutral and throttle in idle position at all times during recovery. All right, what are we supposed to do first according to this procedure? All right, it says immediately move the control column full forward, right? But if you read the last sentence, what does it say? Aileron should be neutral and throttle in idle position at all times during recovery. What do we need to do first? Something with the power in the ailerons, right? But it's tacked on here. It's the very last thing you're going to read. And if, in fact, it occurs after you've executed a smooth pullout, right? And we're intimidated by immediately move the control column full forward. All right? So we have to read into the procedure, be able to interpret the procedure. The other problem we have is the word simultaneous in here. And in the procedure, what NASA found as far as simultaneous rudder and elevator inputs, they found the simultaneous inputs to be nearly as effective as separate inputs. More instances of delayed recoveries were observed in the test airplanes using the simultaneous inputs as opposed to the separate inputs. What that means is it would still recover with simultaneous inputs, but it took a little longer. But also put a pilot in a duress situation where he's sitting in an airplane and all he's ever done in his life is done this, and you tell him to do the rudder and the elevator at the same time, what do you think they're going to do? Well, in my experience, the simultaneous actions tend to be difficult for pilots under duress, and they may result in potentially detrimental elevator-only inputs. All they're going to do is shove the elevator forward. And unfortunately, that tends to aggravate the spin mode, and it deflects them away from their primary recovery control input, which will be the rudder. Okay, so again, having to really think about, well, how do I implement the procedure that the manufacturer has printed in the book? Okay. The last procedure I'm going to talk about is titled, What About the Hands-Off Method for Spin Recovery? Now, a lot of general aviation pilots have heard of some such procedure, and unfortunately, it's come into the general aviation community taken out of context, and I'm going to really describe what the procedure is. When I talk about a hands-off procedure, they're talking about a procedure developed by an aerobatic pilot for primarily aerobatic airplanes, and those aerobatic airplanes being a Pitts or a Christian Eagle. Okay? And unfortunately, the general aviation community got wind of it and said, oh, well, all I have to do is let go of the controls. All right? And they've taken it out of context. The procedure was actually developed by the aerobatic pilot named Gene Beggs, very well known for as an instructor and an aerobatic pilot. But this is verbatim his procedure. Cut the power, let go of the stick or yoke, apply full opposite rudder. So it's not a free release of the controls technique. The pilot still has to do something. He's got to get the throttle off, then let go of the control wheel, and then he's got to be able to identify and step on the opposite rudder. Otherwise, it's not going to work. Well, let's review the pair method again and take a look. Step 1 is power off, 2 ailerons neutral, 3 rudder full opposite, 4 elevator through neutral. And what we find is steps 1 and 3 are identical in the two procedures. Step 2, really, what are we asking the airplane to do? All right, airplane, you move the ailerons, you move the elevator. I don't want to do it. Okay? So we're just dividing the duties between the pilot and the airplane. And if we take a look at a Pitts or an Eagle, in which the Beggs method works very well, and analyze the sequence of events, let's see what happens when we do those 3 steps of the hands-off procedure. First thing, power off. The only way that's going to happen is hopefully run out of fuel in the spin or pull the throttle off, right? Pilot's got to do something. Step 2, let go of the stick. The airplane immediately moves the ailerons. And depending on the spin and how you entered it and how many turns you are, it may go full in spin, it may go partially in spin, or just about neutral. But it'll move the ailerons. It will not move the elevator. You can sit there all you want and stare at the stick, and it's not going to move until the pilot does something else, and that's apply the opposite rudder. Step 3, the pilot must apply the opposite rudder. Has to still be able to identify it and still push it all the way in. As soon as he does that, in a hands-off airplane where it works, the elevator now pops somewhere through neutral to break the spin. So the sequence of events is identical between the two. All right, it's just who does what. In the hands-off procedure, which again was designed for aerobatic airplanes only, half of the duties are done by the airplane, the other half are done by the pilot. In the full-blown pair method, the pilot attempts each of the 4 steps. And in fact, we can take it one step further. If you apply the 4 steps on your own and it doesn't seem like it's working, go ahead and let go. You've got nothing to lose by letting go of the control wheel, because I hope you're wearing a parachute, and at the point you let go, you're opening the door to get out, right? Makes good sense. All right, the last piece of video I'm going to show you will be kind of what it might be like if you actually went through a couple of spins, just to get current again if you haven't done spins for a while, or to just try to explore that corner of the flight envelope that you've always heard about and maybe a little apprehensive about. And this is all point of view stuff. The first couple of scenes will be in a decathlon, seeing what it's like to ride through a couple of spins. And the last one will be an IFR spin recovery, just looking at the instruments. And an IFR spin is different from a spiral in that the spiral, what happens to the airspeed? Increases in a big hurry. Okay, and the altimeter unwinds and the VSI is pegged. In a spin, what happens? Well, VSI is still pegged, the altimeter is still unwinding, but the airspeed is low and constant. That's the key. Low and constant airspeed in a IFR unusual attitude, probably a spin. Power off, ailerons neutral, opposite rudder, elevator neutral. So we'll just take a look at what it might be like to go through some spin training, both in a VFR environment and an IFR environment.
Spin training typically begins with normal upright spins. As the pilot, you'll learn how to enter a spin, maintain your orientation using ground references, and recover on specified headings. Normal upright spins are essentially 1G maneuvers and do not toss the pilot around the cockpit. They feel normal. The recovery involves about a 2.5G pull on the stick or yoke. After just a few tries, you'll even be able to describe your inputs during a spin.
Right rudder stick back, looking for a landmark. 3/4 point left rudder stick neutral, rudder neutral, and then recover it back to level. Nice smooth back pressure. And once you're back to level, feed the power back in.
If you're instrument rated, you can also do spin recoveries under the hood. You'll learn to recognize spins using airspeed and altimeter movements and ignore the gyroscopic instruments. Look at the tumbling artificial horizon and directional gyro. Note the VSI is pegged at 2,000 feet per minute down. The actual rate of descent is near 6,000 feet a minute. The altimeter is unwinding rapidly, but the airspeed is low and constant. Again, you physically feel like you're near normal flight. With practice, recoveries from these situations become instinctive.
I hope you enjoyed the Stall Spin Awareness Seminar. There's a lot of good information available on the subjects of stalls and spins. One such publication we highly recommend is FAA Advisory Circular number 61-67B, titled Stall and Spin Awareness Training. Your local Flight Standards District office should be able to provide you with this free publication. Please review the information in this tape often as part of continued stall spin awareness training as you progress through the various levels of flight instruction. This video, along with solid ground and flight instruction in stall spin awareness, will help you meet and exceed the minimum requirements of the FARs. Better yet, why not couple this with actual hands-on spin training? Believe it or not, it takes less than 2 hours in an airplane to be able to deal with spins effectively. And there's a very good chance you'll enjoy the experience. Be safe.